Okay, thank you. Okay, so let's get started. Uh, yeah, let's assume that you wrote a low-level program in C, such as operating system or hypervisor or firmware for hardware, etc. Then these programs frequently use low-level memory manipulations, such as casting integer to pointer and then accessing memory using that pointer. And then, when they're compiled, they are first translated into compiler's intermediate representation, or simply IR, and then optimized for performance. And interestingly, these optimizations assume that memory has high-level properties, such as no one from outside can access local variables if they are never escaped. And then, here comes the problem. These high-level properties for optimization and low-level memory manipulations are conflicted. For example, you can write a program that actually accesses others' local variables through integer-to-pointer casting. So our goal is to reconcile them. In order to reconcile them, we need to first define what memory is. And a memory model specifies the behavior of memory operations, such as what is the result of load and when store is well-defined. As a result, it determines which low-level programs as well as high-level assumptions for optimizations are valid. And a good memory model should make both common low-level programs and high-level assumptions valid. So let me explain why thinking memory just as an array of bytes and thinking pointer as an index to that array does not explain optimizations. Let's look at this example. First, variables p and q are defined, and the integer address of p plus 1 and q are compared. If they are equal, then 10 is stored into p plus 1, and then q is printed. Compiler can optimize this by doing constant propagation. Here, the initial value, constant value 0, is propagated into the print statement because variable q is nowhere modified between these two places. And note that I'm using C syntax for LLVM intermediate representation code just for readability. Now I'm going to explain why thinking memory as a byte array cannot explain this optimization. Let's assume that P is at address 100 and Q is at address 101. And then this integer comparison becomes true because both IQ and IP are 101. So this statement is executed and P plus 1 has address 101, so it successfully updates the value at address 101. And then Q0 also has address 101. So finally, this program prints 10. However, you can see that constant propagation modifies the behavior of original program into the one printing 0. And this is undesirable because optimization should preserve the behavior of the program which is written by programmer. And the underlying problem in here is that local variables like q can be accessed from local variables like p by pointer arithmetic if memory is just a byte array. In order to resolve this problem, we can give abstract structure to memory, and this is how C standard defines memory model. Rather than defining memory as a byte array, we can think that memory is a set of objects. So here, in this example, there are two objects, which are P and Q. And each pointer tracks which object it is pointing to, and this is called provenance. Now again, integer comparison IQ and IP becomes true. So this statement is executed, and here, P plus 1 has provenance P. And this statement tries to update the value at address 100 with provenance P, but it fails because there is an object Q at address 101. We say that this kind of illegal operations have undefined behavior, and there are two principles for the notion of undefined behavior. First one is that compilers assume input programs never raise undefined behavior, so compiler can freely optimize it into any form in this case. Second, programmers should not write programs raising undefined behavior because it has illegal operations. Okay, so I've explained how having the abstract structure of memory as well as giving provenance to pointer explains this constant propagation optimization. However, the problem is that there exist optimizations in compiler which cannot be explained if there is a provenance in the pointer. And furthermore, it may cause miscompilation in certain cases. In order to show that, let me extend the previous example by adding two more optimizations, which are integer equality propagation and cast elimination. First, integer equality propagation replaces IQ with p plus 1 casted into integer. It is possible because IQ equals IP and IP equals p plus 1 casted into integer. Second, cast elimination removes two casts, which are pointer to integer casting and integer to pointer casting. Third, constant propagation optimizes the code as explained in the previous slides. So each optimization seems valid, but end-to-end miscompilation already happened in this example. After optimization, the program is printing 0, but before optimizations, the program is printing 10 because IQ equals Q casted into integer. So this statement correctly updates the value of variable Q into 10. The reason why miscompilation happens here is that there is only a weak consensus about what pointer is between these three optimizations. Furthermore, we found that this miscompilation happens in both LLVM and GCC, meaning that modern compilers are suffering from lack of sound memory model. So the goal of this paper is to find a good memory model for low-level memory manipulations, such as pointer integer casting for compiler IR. Okay, so I'm going to explain what are the details problems and what are our solutions. Problem 1. What is the semantics of pointer to integer casting? Let's assume that pointer P has provenance P and address 100. Then for the integer casted from pointer, we have two choices. First one is that the resulted integer also carries provenance, meaning that integer and pointer are totally equivalent. Second choice is that the pointer to integer casting drops provenance, so integer now becomes pure integer, but pointer and integer are now completely different. We chose the second option, and I'm going to explain why the first option is problematic. A problem with carrying provenance is that it does not support useful integer optimizations. So if I equals j, then k equals I. But also k equals j because I equals j. So it is the transitivity of equality. If I doesn't equal j, then k also equals j. So compiler can optimize this into just k equals j. So this seems to make sense. But let's assume that now integer starts to carry provenance. So let's assume that I carries provenance p and j carries provenance q. Then I equals j comparison becomes true because integer comparison should be well defined. So k has provenance p. However, after optimization, now k carries provenance q. In conclusion, the problem of carrying provenance for pointer to integer casting is that this kind of integer optimizations may change provenance, thus it may change the behavior of the original program. But if we choose to drop provenance, then integer just becomes pure integers. So now this optimization becomes sound. Okay, so far I've explained the semantics of pointer to integer casting. Now here's the problem 2. What is the semantics of integer to pointer casting? Let's assume that there is an object P at address 100. Then for the pointer casted from integer 100, we have three choices. First one is that the pointer has empty provenance, meaning that we cannot access any object using this pointer. Second choice is that we give the provenance depending on the memory layout. So for example, if there is no object at address 100, we just give empty provenance. But if there's an object P at address 100, we give provenance P. Third choice is that we give always full provenance, meaning that we can access any object at address 100 using this pointer. We chose the third option, and first of all, I will explain why the first option is problematic. A problem with first option, giving empty provenance, is that it does not support common program pattern which involves pointer integer round trip. So let's assume that there is an object P at address 100. Then this pointer P has provenance P. But integer I is a pure integer because we chose to drop provenance. And P2, which is casted from integer I, now has empty provenance. So the last statement raises undefined behavior. But this is undesirable because this kind of code pattern is widely used by C programmers, so we cannot give undefined behavior to this code. So the problem of the first option is that common program patterns raise undefined behavior. But if we choose to give full provenance, then P2, which is casted from integer I, now has full provenance. So the last statement can successfully update the value at address 100. So if we give full provenance, then this kind of code pattern can be explained. Okay, so I'm going to explain why giving provenance depending on the memory layout is problematic. A problem with giving provenance depending on the memory layout is that it does not support reordering of instructions. Let's assume that malloc call created an object at address 100. Then Q in the original program has provenance P because there is an object P at address 100. However, after the program is reordered, the malloc call has not been called yet. So Q has empty provenance because there's no object at address 100. So you can see that the behavior of the original program and the optimized program is different. So movements of cast or function calls including such cast is restricted, and this is problematic because we cannot support any useful optimizations like loop invariant code motion. But if we choose to give full provenance, then Q in both original and optimized program have full provenance, so the behavior is equivalent. So giving full provenance not only supports reordering, but it also supports common program patterns, so we choose the third option. Okay, so far we've described the semantics of integer to pointer casting and pointer to integer casting. Here is the third problem. The third problem comes from having full provenance. Now, anyone can modify others' local variables by guessing their addresses and acquiring full provenance via integer to pointer casting. So let's look at this example. Here, variable P is defined and initialized with 0, and unknown function f is called, and finally, the value of Q0 is printed. With constant propagation, we can optimize this program into the right one, which directly prints constant 0. But let's assume that P has address 100, and function f is trying to update the value at address 100 with 1. Here, you can see that function f is using integer to pointer casting to get full provenance to address 100. And also, it is guessing the address of local variable P. Finally, the value of local variable P can be successfully updated by this unknown function called f, so the behavior of this original program is printing 1. However, again, constant propagation changes the behavior of original program into the one which prints 0, and it is undesirable. So we cannot explain constant propagation again. In order to resolve this issue, the basic idea is to exploit non-deterministic allocation. So the address of P not only can be 100, but it also can be 200 as well. So let me call these two executions 1 and 2. Then in execution 2, this code of which is in function f raises undefined behavior because there is no object at address 100 in this execution. So source program again raises undefined behavior, so we can explain this constant propagation. We formally define this idea using a notion of twin allocation. Each allocation, such as declaration of variable P, creates two objects at memory and non-deterministically marks one of them as invalid. So for example, we can choose the block at 100 to use and mark the one at 200 to be invalid. In another execution, we can mark the block at address 100 to be invalid and use the 200 one. In execution 2, guessed access, like the second statement, raises undefined behavior because the block at address 100 is marked as invalid. Like this, whenever there is guessed access, we can find an alternative execution which raises undefined behavior, so we can explain constant propagation. However, important point is that this argument works only for unobserved addresses. So in order to clarify that, let me give you an example. This is the example from previous slide. But now I'm going to observe the integer address of P by introducing this if branch. Now you can see that the P is twin allocated, so it has two possible executions. But in execution 2, this if branch is never taken, so the guessed access at the third statement is never executed. Therefore, undefined behavior does not happen in execution 2 anymore. Therefore, again, we cannot do constant propagation again. However, this is okay because compiler already does not optimize this case. So twin allocation is consistent with common compiler's assumption, which is that observed variables can be modified by some unknown accesses like the third statement. Okay, so I've described the semantics of various operations like integer to pointer casting and pointer to integer casting and allocation. So let's revisit this miscompilation example again. There were 3 optimizations, and the culprit of the miscompilation is the second optimization. Of variables equivalent, which will make vectorization possible. So we recover performance by reducing unnecessary casts among them. So we could remove majority of integer to pointer casting and pointer to integer casting. Our paper includes more details and also a formal specification of our memory model. Okay, so far I've explained my memory model, and I'm going to briefly explain how we implemented it and what the experimental result is. We fixed LLVM 6.0 to be sound in our memory model, and this includes removal of illegal operations, illegal optimizations such as cast elimination. And while doing that, we only had to change about 1.7 thousand lines of code of LLVM in total, meaning that our memory model is quite portable. And also benchmark results show that our memory model does not cause significant slowdown. And also we verified key properties of our memory model in Coq, which is a theorem proving language. So in conclusion, we developed a memory model for compiler intermediate representation, which supports both low-level code and high-level optimizations. In order to do that, we use several key ideas, such as full provenance and twin allocation, to reconcile them. Experimental results show that applying our memory model to LLVM has only little impact on performance. Yes, thank you for your attention.
In the last example, you can just go back to that slide.
This one?
Just further back. Yeah, so here you said that the compilers don't exercise any, like they don't do constant propagation because the value of P is observed.
Right, and it is observed, and also there is unknown access. And
right.
So, yes.
And if you go back to the main example which you're looking at in the beginning, the IP, IQ.
Yes. Oh, sorry.
Sorry.
Okay, so maybe I can directly move to the slide. Let's get this one.
Yeah, so here also the value of IQ is observed, and there's
Right.
an unknown access, so
Right, there's no unknown access because we can guarantee that p plus 1 accesses object p because p plus 1 carries provenance. But in the later case, it is accessing the pointer which is casted from integer. So basically, it does not know which object it is going to access. So it is the problem.
okay.
Yep.
We have time for another question.
Yeah, so in this example, don't you already have undefined behavior because you're accessing outside the bounds of P?
Yes, so it should have undefined behavior in order to support this optimization. And we have to explain why this raises undefined behavior.
Because you're accessing outside the bounds of P.
Sorry?
You're outside the bounds of P. You're going
Yes, right. Yes.
So that's why it's undefined.
Yes. So if pointer is just an index to some byte array, then p plus k, there is no information about like p plus 1 is should point to the inbounds of object p or that kind of thing, right? So basically, that is why C memory model is defining memory as a set of objects, and each pointer is tracking which object it is pointing to. So yeah, it is how it finally raises undefined behavior.